And so I'm just going to introduce my community a little bit, and then we can get started. My name's Annie. I'm one of the founder for my community called Intelligent. And I don't think this clicker. Okay. Yeah, so I'm the founder of a AI community called Intelligent, and what we do is that, so we are a community that we want to help founders to connect with CMU talents. We are officially collaborating with CMU entrepreneurs, and we are co-founded by all of the CMU alums. So I have one co-founder over here. Her name is Alina. She's joining Speak as a PM soon, and another volunteer over there. He's still in school at CMU, and then I'm the founder of it. It's my side hustle. I do work for an AI company as a PM, and we do help founders and builders to connect together, and we host offline events and online sessions. So if you are interested in any of our events, just feel free to scan the QR code and follow us. And we're going to host more events like this. We're also welcome any partnership in the future. But yeah, without further ado, I want to introduce another host from LanceDB.
All right, thank you, Annie. We can go back to the speaker list. I want to talk about how awesome they are. Oh, actually, the second page is fine. So they can see all of those. You guys are gonna see the speaker's face, so I guess we don't have to flash their face. My name is Jasmine. If you haven't met me yet, very nice to meet you guys in person. I've sent some of the LinkedIn connection with you guys. I would be happy to connect if you tell me who you work for, where you're working at, what you work on. If there's any chances for collaboration, I'm all down for it, as long as it's good work. Right? I do have a pretty good panel today, and I'm honored to have all of them. This is the list today here, but before I even introduce the panel, I want to give a good shout out to Annie and her team. They are a nonprofit CMU alumni started, and they really helped me a lot to put this event together. And then aside from Annie, I do want to give a big shout out to the Anyscale office management team. It wouldn't be possible. I basically borrow their office, I borrow their equipment, I borrow their water. So everything that you guys see here, it wouldn't be possible without them. And then I almost blew up the event by having too many guests. So I guess we're okay for now. And thank you guys for showing up early, as we expected, from a good audience. All right. So we have, I know on the poster we have a few speakers listed up. I'm not going to be a speaker. We have all technical, folks there. I don't want to go too deep and dive into what work they did, but chances are, if you guys understand what journey it takes to become a Apache member, you got them in this speaker list today. They're the OG of open source. Chances are, if you worked with any data info tools, those are the creators and major contributors who started or guided or merged your PR. So those are the ones who you're listening from. And I've also collaborated with those folks in my previous companies, in the company before that, and in my current company, LanceDB. So I'm pretty honored to have all of them here. As you could tell, we put this together as a multimodal AI in production. That's what we're aiming for. So as we're stepping into the next generation, we all see the environment is changing. We're stepping into a new era. So Ray, I haven't seen any AI company that did not use Ray yet or are not aware of Ray. So I'm pretty happy that we have the Ray team here to share with you guys how, what their work. And of course, LanceDB, we're actually actively working with the Ray team to make things better. We announced, if you followed us, you saw that we have the Lance Ray read available. We're also doing more things. You should expect more coming from those two teams' collaboration. And at LanceDB, we're a relatively young company. How old are we? We're a year old. We're 2 years old. Yeah, we're a little younger than that. But Lei is my colleague and a CTO. I can introduce him a little more later. So at LanceDB, we built the foundation for Multimodal AI, the Multimodal AI. We built a database. We come up with a Lance format. Lei will probably dive a little more into it. So LanceDB is currently being used by a lot of Gen AI companies. Feel free to check our website, our GitHub, our Discord channel, and that's where you're going to find us. Our third speaker is going to come from an old friend of mine, Rong from Character.AI, a pretty hot startup right now, also in the Gen AI space. That's one of the company that has the, sort of a 2C product among today's speakers. Last time when I worked with him, he probably went lightning speed, both on his working and coding style and also on his speaking style, even faster than me. If you think I'm speaking fast, you wait until he starts. We can ask him to slow down if it gets to it. All right. So without further ado, this is agenda. Anyscale will go first, and LanceDB and Character.AI, so we can tie that. I did say our speakers all put a lot of effort into both building the technology and preparing for today's talk. So let's not interrupt them while they're giving a talk. We allotted about 20 minutes for each presentation, and after each presentation, you'll be given Q&A time. We'll throw around that catch box so when you catch the box, you're allowed to give that Q&A. Because, and for our speakers, they need to repeat your question just because we're also doing a Zoom recording before they answer that. So try to make your question short and sweet instead of a long statement, right? And then afterwards, we'll leave you guys some time for social networking until our office manager kicks us out. All right, that's about it. Let me introduce our first guests, speakers. Joe from Anyscale, head of open source still. Yeah, in the Ray team. And then Chung from the Ray team.
Hey, thanks, Jasmine. This works. This works. Which way? Hello, everyone. My name is Joe. Yeah, from Anyscale Ray team. Today, Chung and myself are very happy to talk about Ray and Ray data. So, yeah, we have a kind of packed content, so I will be short in my part. So I will give a really general and brief introduction of the Ray framework, and then Chung will dive deeper into the Ray data component and why you should use it. So yeah, Ray overview. So the first slide I want to show is to kind of really quickly give you an impression what is Ray. So the TLDR is that Ray is a really quickly growing distributed computing framework. In this chart, I'm showing the growth trajectory of GitHub stars from the time these projects were created. I'm listing Spark, Kafka, Kubeflow. Many of these are kind of created earlier, so you probably are more familiar with it. You can see that the trajectory of Ray has surpassed Spark a few months ago. Right now, we're going at a really quick speed. Another highlight I want to show is that yeah, OpenAI has been using Ray for all their large model trainings. So this is from Ray Summit 2 years ago. Greg Brockman, the president of OpenAI, talked about their usage of Ray. I think the highlight part is that, so OpenAI, if you think about it, they need to iterate really fast in their model logic and data processing, but they need to iterate fast at a very large scale. With previous generation computing frameworks, it's really hard to meet these two requirements together. You have either one, you have to choose. But Ray allows them to achieve this goal at large scale, and they compared many, many frameworks, and Ray owns a whole layer, but not in an opaque way. So, so in the next few slides, I will provide some more technical detail, hopefully to give you an overview of how to use Ray. So the short version of what is Ray is it allows you to run arbitrary Python code on a cluster. So here I'm showing a piece of Python code. It's very simple. It's nothing distributed. You define two functions. The first function will read a file into an ND array. The second function will add together two arrays. You get a result. In the main part, you read two arrays from two files. You get a result. Right? Very simple. I think the question is, how do you leverage the computing powers from multiple nodes to finish this faster? So the answer is you can use Ray. So the modification to the Python code is really simple. You first decorate your Python functions with these simple add, read, or remote. After decorating these Python functions, they become executable units to a cluster. And then when you actually execute the, the Python functions, you do you do dot remote. By running these tasks are submitted to the clusters. And here I'm showing a diagram to show what kind of, how it works under the hood. So when this line is called id1 equals read array or remote file 1, this task is only submitted to the cluster. So similarly, when the next line is called, you submit another task. So by doing that, you can parallelize these two unit work to two different nodes. you're utilizing the CPU memory resources on these two nodes concurrently. And then when doing another function call, again, we submit a task instead of waiting for this task to finish. This is similar to how you do thread pools and other asynchronous computing. Only at the last line, when you do redoc get, this is a blocking call. Only at this step, you wait for this computation to finish. By doing that, you can write mostly regular Python code, and you can utilize the computing resources on a cluster. And I think you might ask questions, so why does it matter to me, right? So I'm illustrating this with an example. It's one of my favorite examples from the community. So imagine you're an engineer in an ML infra team, right? So you acquire a pool of GPU resources, and you need to service like tens of data scientists who want to use this pool of GPUs. So using Ray, how to implement this is much simpler and much more elegant than previous generation computing frameworks. You just start a cluster with a given number of GPUs, and every data scientist, when they want to run jobs, they just specify the amount of resources they need, and then Ray takes care of scheduling and fairness, fault tolerance, and all that. So one feature which is becoming popular is you can even use fractional GPUs to allow more fine-grained resource allocation and higher utilization. So hope this gives you an overview of what Ray is and how you can get started with the real kind of one-on-one hello world. In the next part, Cheng will give you a deeper dive into Ray data.
Give a little bit. Okay. Give a little bit of the background of ML data processing. So basically, for any ML data processing, they have like several steps that is required. The first step is people need to read the data from the cloud storage. So we are talking about millions of files, terabytes of data sets, and it can have different data format such as image, video, audio that become one more popular and more traditional. People use Parquet, TF record, JSON-L to store the data. And after reading the data from the cloud storage, next step is to transform the data with arbitrary Python function. Because the data scientists, data engineer, and ML engineers, we are all used to like use the Python function to do the processing. So there's two categories of the functions. The first one is stateless, which is running in background in parallel. It can be a map to run a UDF function and filter some of the data flat map sample. And another category is stateful, which means people need to shuffle the data across multiple nodes, do the sort, do the group by, aggregate, join, etc. After doing the transformation, the last step is to move the data to the model efficiently. Here we talk about training and inference. That all come to require the heterogeneous cluster to do the data transformation in a streaming way from the CPU to the GPU. In the meantime, people want to make sure the GPU utilization being pretty high. That's because the GPU is most expensive compared to the CPU and the memory. And the people do not want to overload the memory, cause a lot of memory issue or any like memory spilling to the disk. So this is kind of common like steps or characteristic of the current ML data processing. And we can talk about some like existing solutions on the industry. And the first category is for the PyTorch ecosystem. PyTorch have their data set and data loader, which being used popular across a lot of like ML workload, but it's not perfect. It have a very bare minimal interface and require people to write a lot of code by themselves from scratch. So there's different like repositories in the PyTorch community. One is the Torch data, another is Torch Arrow, which is provide richer APIs on top of like PyTorch dataset, but it also have the functionalities that people can do the data manipulations and etc. The problem with these two libraries is they are not like designed for the distributed data processing. So mostly it's still the local development on a local single node. So there's the in-place replacement for the touch data and touch arrow, which is a mosaic streaming dataset and web dataset developed to like building on the distributed system. After the PyTorch, TensorFlow also have their TF data implementation, which is mostly the previous generation. And the Hugging Face, they serve all the dataset on the Hugging Face hub, mostly serving as the hub to serve a lot of different dataset. People upload the dataset, people can download, but mostly still a single node setup. More traditional for the ETL workload, people use PySpark and Dask, which is first designed for the ETL SQL analytics. People also use PySpark and Dask to do some of the ML data processing workload. For the read data at a very high level, we want to introduce the class called the dataset. This is a major class of the read data, which is a distributed collection of the data objects, and it supports the read and write. So we support different data format, Parquet, image, video, audio, JSON, CSV, etc. And it can work on different cloud setup, AWS, GCP, etc. In the transformation, it supports the two different types of the transformation, stateless, which is map batches, map filter APIs, and similar for the stateful, it's supposed to shuffle the data randomly across the nodes and sort and aggregate. Finally, for the iteration, when people want to convert the data from the CPU to the GPU, provide two different iteration API, it can convert to the best format people want to use, such as Torch Tensor for the PyTorch, Pandas, NumPy, or arrow format. And besides on that, it also supports a set of the debugging APIs to show limit, tick batch, or iter rows to the local development. And it has an integration with the rest of the ecosystem, can convert to a PyTorch data loader, TensorFlow dataset, Hugging Face, and PySpark. Here I give a link of the 4 APIs for the reference. To make sure we are like on the same page for the on the code level, I just walk through guys for simple code examples. How do we do the ARM batch inference with read data? So do the ARM inference for the offline data. The first step, you need to load the data from the cloud storage into the cluster. Here, assuming the data is in JSON format, but the data can be in Parquet format, text format, or other different format. The first step is we have a read data, read JSON APIs, and people can like set the arbitrary S3 buckets into the APIs, and the return value is a data set, which is representative of all the data from the S3. So at this point, nothing has been executed. The execution has been triggered to read the data yet. It just remembers the metadata and it will be triggered later. So the next step is people can plug in any arbitrary functions to transform the original data, transform the JSON files, such as you want to extract some of the text prompt from the JSON file or with some like metadata. The function here is arbitrary Python function people can define. The next step is after the reading that we want to define the class to do the actual inference. Suppose you have a large language model you want to use here. Here we use Mixture 7B, but we can also plug in any like larger models such as Mixture 8 times 7B and the Llama 3 70B also supported. In the init function, it's passed in a RM object. The RM object here is from the VRM repo. VRM is a open source RM inference project. I will not get into the detail here, but you can either initialize a VRM or TensorRT RM object. And in the call function, you can invoke the generation function of the underlying RM engine that to run the inference on the batch of the test data. Here, after the call, it will get the batch of the output from the test file. With this code, all the GPUs will be launched and distributed execute in parallel across the cluster. So imagine you have a terabyte of data, you want to do the LLM inference, such as you have all the articles and you want to do the summarization of all the articles to get the highlights. So you have this task. You can run the read data with your input data, just plugging with this code example to starting from here. So we provided like 4 working examples in the VRM repo, which is using read data to do the distributed offline inference. And regarding the supported models, Llama 2 7B, Llama 3 8B, and Mistral 7B, those small set of number models are all supported. And the Mistral 7B currently is already supported on the Anyscale, and we plan to open source it. And here you can see a full list of the models. It covers most of the LLM model popular today. I will just get a little bit like introduce a little bit concept of the read data. I will not go into the details, but at a very high level, how it executes the operators, it will build a DAG of the execution plan of the operators. It will model the read, map, and the inference as different operators and building a DAG of that operators. And also it has optimizations to fuse the operator together to give the best performance. Under the hood, it has a streaming executor, which is reading the data in a streaming way and pipe the data through the operators with a queue-based backpressure policy. So that's how it achieves the streaming execution across the pipeline without causing any or any memory issues, but also maintain the GPU utilization to be very high. And it also have a asynchronous multi-threaded module to move the data from CPU to GPU. So when the current batch of the data is being processed by the GPU, the next batch will be immediately available for the process on the side. During the data transformation, supported 2 different memory formats. One is for the arrow table, arrow format, and also another is pandas data frame. So either people use arrow table or the panda data frame, all the operations are very efficient without any further data copy across the operator. During the iteration, suppose the touch tensor and the numpy ending array, it can directly hooking plug to the uh, touch training functions of the other TensorFlow training. Talk a little bit about use case for the batch inference here that you want to do the inference on offline of data. We already have the users from ByteDance, Instacart, Airbnb, all these big companies. They all build out the solutions on top of read data for the batch inference that they want to do the model inference on the large scale of the offline data. Here we also compare the performance of the Ray versus other popular systems such as Apache Spark and AWS SageMaker, which gives the detail of how the rays give better performance on the offline inference. Specifically for the multimodal data, which has a new challenge. I probably know a lot of people here already know that OpenAI has announced yesterday that which is quite amazing. You can talk to their new GPT model and they can understand video, audio, etc. So multimodal is really pose the new challenge for the new system, and it invoke a lot of large scale distributed system problem. So Ray plus LanceDB here is for the rescue. First, for the LanceDB, Lance is a modern columnar data format for the ML, and the LanceDB is the database built on top of Lance to give the best performance of multimodal AI. With Ray data is the framework. They can reading from the Lance and also inject into the LanceDB for people to use. So it is scalable, the distributed compute engine for the multimodal AI workload. So you can learn more from the Lei, the CTO of the LanceDB in the next session for the LanceDB. That's all I have today. Yeah, feel free to take any question. Yeah. So the question is, we talk about the offline inference for the Ray, and what are any like advantage for using Ray for the online inference? So for the online inference, Ray developed a library called Ray Serve, which is provide like very scalable like online like with fault tolerance the solutions to serving the online data. So it doesn't cover the read data is only for the offline. For the read server is for the online, and it also provides a lot of like functionality versus other online inference service, which is not covered here.
Just to add a little bit, I think one scenario where reserve is especially strong is what called inference graph. If one single request needs to go through multiple models or a combination of models and the business logic, then reserve is more flexible and more powerful than other streaming frameworks. In general, the more flexibility you need, the more you can benefit from using reserve, like inference graph, model ensemble. Happy to share more. So it's relatively early, but we do have some support. Happy to share more details.
The question is for like working on the petabyte scale of the data, what's the like GPU utilization we can push? Is it 80% or 90%? So I can share like more detail of the current like GPU utilization. So for the ARM batch inference workload, we are seeing like about like 95% of the GPU utilization across course of like 10 to 20 hours for typically like large like ARM workload. So I would assume for the petabyte scale, we can still push to the 90%, which is like scale linearly with the current ARM offline inference. Of course, with the petabyte scale, it will like pose more challenge into the system. For example, when we talk about the join to the group by to the aggregation to the shuffle stuff, of course that part will not be scaled linearly. It will like cause more issues. Specifically for the ARM batch inference, it's not the case here because mostly people like reading the data and do the inference in parallel without any like cross-node communication. So the question is, given the GPU resource is so scarce today, is it possible to do the multi-cloud setup, like run a workload across multiple different cloud providers?
I think the short answer is there's an open source project from UC Berkeley called Skypilot. I highly encourage you to look at that project, especially if you use that together with Ray. Skypilot.
Right. Before I call layup, if you guys want to move in, like there's still some space there, because in case if you want to see like the slides, if you guys don't mind, have new neighbors, if they wanted to sit next to you, please be kind. Then I can call Lay in. All right, like I said, I'm not going to be a real speaker because I didn't write a line of code. Those people did. That was many, many years ago when I committed. So I have Lay. I do have a good intro for him because I've been working with this guy for the past 2 months. I am relatively new to LanceDB as well, even though it's a pretty new company. And I'm pretty humbled and feel really fortunate to be his coworker. He doesn't he's probably one of the most down-to-ground person and a funny person in our company. So it's pretty cool. I like it. And then him and his team, they lead a really fierce team to really make everything happen. Pretty easy for me. So I do want to give a good shout out. He's going to give you a good intro on LanceDB, which is a thing that he wrote probably a year ago. Here you go.
Okay, thanks for introduction. So I'm the CTO of LanceDB and built this thing from about a year ago, so it's very young. And we are one of maybe the latest to actually get into this vector DB market. But we have maybe learned from a lot of other companies, and we have learned a lot of experience from error and trials from our customers as well. So today's topic is about how we deploy LanceDB and Ray in an actual production environment for multimodal AI company. Before that,
Make sure this is on. This is on. Maybe closer.
actually, can you hear us? Okay. No. Okay, I will try to speak louder. So I think it's a little bit lucky for us when we actually get into this market. That's where ChatGPT start to blossom in this market. And at that time, we see the market very different to maybe 2 years ago, 2 years before last year, that people see different use cases. And we have seen a lot of generic companies, and we feel their pains, and we actually share many pain from our previous working experience. So for multimodal data company challenge engines, the first thing everyone will think about NVIDIA. But other than NVIDIA, there are more challenges for them. For example, we have very lucky to work a few very good companies out there. They are doing, say, text-to-image, text-to-videos, and code generation, among other multimodal applications. And they have a lot of them have petabytes of video, image data, PDFs, prompts, embeddings, and all that. And they just realized that there's no existing solution that's as good as our old days for big data days that everyone knows how to manage these terabytes of data, where everyone have a consensus that this should be the good way to manage those kind of data. So that we realized that between all the companies we talked to, there's no two companies actually share the same stack or share the same practice. And the problem of that is like in every company, there are AI and machine learning engineers will become the first line of defense to drive the decision of what is a good data infrastructure or machine learning infrastructure, where they sadly miss 10 years of best practice from the previous generation of data infrastructure. And many of those companies start from the model, from the idea, from very awesome demos. Then they see the adoption of their use cases, and they start to put things into production. At that time, the infrastructure to support this company become afterthoughts. And there's a lot of time people start to ping us to see what would be something out there that we can use. And for multimodal AI, or even the AI before multimodal AI actually, or ML, have many stages of different activities to actually push an idea to the production. And those activities usually including, say, data curation, exploration, training the data, and serving the data in some forms. And maybe a lot of users, a lot of audience here that have seen your companies building a Parquet, data lake, or iceberg-based source of truth to contain all your training data. However, those kind of data is not good for data lake. It's not good for storing the multimodal large blocks of data because it's not. It was designed 20 years ago. That designed for completely different use cases. And another thing that's super challenging is like for feeding your GPU, because GPU is so sparse in the market, you need to feed a high utilization of your GPUs. Then the training and the shuffling of your stage of your training pipeline become very challenging. However, all the people we ask for, they say they want this tooling as simple as 10 years ago, just use a pandas or polars or SQL. And when we, from the storage or database people aspect, we categorize the AI I/O characteristic into three different aspects. The first one is like, because multimodal data we need to support videos and images and text. We want to store and manage large blobs in these systems. And we need fast scan to fully utilize the GPU doing training. And we need random access to support shuffling, sampling, or even the exploratory activity for you to debug a model. However, we don't see anything in the market that can actually deliver three of them. Because of that, there are, at least from our experience, many companies start to build multiple single-purpose systems to satisfy different workloads. And each one of them is optimized one access patterns, where you have a data lake just as a source of truth, and many of ETL pipelines to dump those data into other forms. And that's where you have a big data infra or ML infra team, where you have another data team just to help the AI engineers to transform the data from one form to another form. And AI, from our user surveys, that a lot of ML AI engineer will say that I just want to do my models. I don't want to learn this language, that framework, just run distributed jobs to help me transform from, say, one tensor to another serialized bytes arrays. However, this is maybe applicable to many of our customers and the user we see in the white. So with all the consideration and the user survey we have, then we think that whether we are be able to actually, from the ground up, to rethink this problem and to rethink whether today's architecture or data infrastructure is suitable for tomorrow's needs. So that's where we come out. We designed the LanceDB from very ground up, just on top of S3 or GCS or file system, that we want to have this full stack implementation to optimize for these three aspects of workloads. And one product can deliver all three. Actually, magic happens. So there's one user code to us. It's like they are evaluating LanceDB as a vector database in the beginning until some other ML and AI team tell you this is actually good for machine learning training and for feature engineering within the same system. So that's where they are super happy. They try to, instead of build two separate systems to to adopt different workload, they now can just have one single system, eliminate a lot of derived data from the company. So LanceDB in a nutshell, it's a developer-friendly open source multimodal multimodal database for AI. It's the first rule that we developed in-house because our team came from Pandas original authors, HDFS, Apache Arrow, and a few other user-facing open source projects that we care developer dearly. So the first thing that we focus on is developer friendly. At that time, we don't even go for the scale or for anything else. We just for this thing should be the simplest one in the market, and you should be already familiar with the interface that you know from 10 years ago. And based on that, we build on top of Arrow, and the data frame-based API is very similar to Pandas and the Polus. And we have a very consistent API across different languages. And with that, underneath, we have a capability to do simple SQL filtering, vector search, flex search, and some other forms of search combined. And it by itself is an open source project on GitHub. And it starts with an embedded database that is as easy as SQLite or DuckDB to be embedded with your different language of applications that you can just go there to play with. However, we do have a very hyperscale of record that is thanks for our early decision to do compute storage separations. That's the lessons we learned from last generation of infrastructure. And with that, we almost see linear scale because all the query or database node is actually stateless with the system, and we can deliver some very challenging, deliver the performance in very challenging environment. And another good aspect of this compute storage separate design is that at beginning of last year, we were the one that actually put all the index in. We serve all the index from the cold storage, where make us like 100 times cheaper than our competitors in terms of cost performance ratio. And if you think that in deploying to several multi-tenancy environment where you only have 5% of active users within that, this actually deliver very interesting cost-efficient ratio to the customers. And we have some other installation is actually not think us as a pure vector database, but as a full end-to-end service systems. They use the vector search as the query language to serving images and the videos and something else that we cannot talk about here. So the LanceDB performance is actually built on top of Lance columnar format, which is an in-house designed columnar format that we learned from about 20 years of experience before this thing. And by itself, it's have three different aspects of the design. Firstly, it's a file format that this piece is very similar to Parquet or ORC. It's a columnar format for fast scan and fast training. However, the main differentiator of this thing to Parquet or ORC is that we provide almost constant time random access. That thing alone, in the beginning, we didn't realize how big this opportunity is until that we start to build other stuff on top of it. And then it significantly set us apart from other columnar formats, basically. And from table, and also itself is a table format. It's similar to Iceberg or Data or Houdin in the sense that we support versioning and we support zero copy schema evolution and wall LSM and all that. And the interface of that is built purely on top of Apache Arrow, which make us quite easy to integrate with any Arrow compatible systems. And I guess the main motivations behind why we build this as a table format itself is like we re-implement or redesign an execution plan on the table level that is specially optimized for random take or random access of large blobs of data, which is super helpful when you have a few billions of petabytes of LiDAR sensors, images, videos, and all that. And based on these two, we start to build index as a prototype to demo our advantages. Then we realized that we can build very good vector search on top of it. And up to today, we can support 3 types of indexing mechanism, like scale index, vector search, and also text search. So the ideal world we want to achieve is that we will have a single source of truth where to serve different retrieval mechanisms. For example, if you think you are text to image or text to video companies, you have a giant table that you have a few metadata columns. You have text columns and video columns, just all of them stored in line with it. And then you have a few other vector columns as your feature engineering columns. So for this, for SQL-based search, we can just scan on our Scala index or scan on this thing with page-based stats and file-based stats. It's very, very fast, and we have a pointer to basically point to any large blobs there. And for machine learning training, we have PyTorch training data loader to actually just scan these 2 columns with a large stripe of HTTP, IO to S3 or GCS. And then similarly, we can do vector search with the index and point back to retrieve the content. So everything of this, when you do the search, it's just become one single search string to actually retrieve any arbitrary arbitrary fields with your basic queries instead of go to different retrieval engine to glue them together later. So luckily, we are built on top of Apache Arrow because Apache Arrow OG in our team, and our blood is very Arrow blood. So this open source in-memory standard help us to very easily to integrate with other systems. For example, today, thanks to Anyscale, they are awesome team that help us to deliver the Ray integration just within a week. And we have PyTorch, Spark, Trino, and among other integrations as well. So this case study is like why we use LanceDB-Ray in production for some generative AI companies. So since Ray 21, Lance source is available in Ray, so you can just use a native Ray experience, actually read Lance in a distributed way. And the Lance is designed very similar to Parquet or Iceberg in a way that you can easily to find the fragments and split that out into a distributed environment and support columnar predicate and filter pushdown as well. And we also have a data sync in working that we can just from Ray data directly read something, process in memory, then write a large amount of data into Lance. And the Lance, because versioning and all that, we support distribute, write, and commits just under this simple interface. And another thing that Lance support and many of our multimodal data company likes is the schema evolution in a way that it can do schema evolution without extra any additional cost. That, for example, you can add a column which only add this piece of data into the system instead of copy your original 10 columns of video to another materialize into another system. And this, for example, you can, this is actually almost a real use case that they just use this to generate embeddings. And they merge a column using existing data set and return a parallel table with the name of the column, then that's it. That's how easy that is. So with Lance and Ray and PySpark integrations, we actually be able to achieve that within this full AI development cycle. They store everything in the same place, and just both in terms of training and in terms of feature engineering and data generation, they can just store in one single source of truth without ETL, and there's no much of a derived data that you need to debug later on. And thanks for Ray, we do have a few unfinished items here. First thing is like we will support streaming writer, which will more efficiently support larger than memory writes per unit in Lance. And we are integrated with Ray as our embedding generation infrastructure. LanceDB itself supports the embedding functions that you basically declares this column is generated from the other column with this API. Then we will automatically generate the embedding for you. For example, today we support OpenAI for that. But with this, we can support your own models, and then we can run that within our Anyscale infra. And other than that, if you're familiar with our vector database, the indexing of vector database is actually super I/O and CPU intensive task. So that's where we utilize Ray fast for distribute training of our index. Okay, thank you very much. And this is our website and our GitHub links. Our cloud is in private beta, and we are currently hiring. This is our Discord. Please, if you are interested, please join. And any questions?
Yeah. Whoever catch me, throw that to whoever has a question. Oh, someone in the back.
And for text-based systems, you recommend RAG versus, there's a debate going on with semantic search versus RAG in terms of accuracy. Can you talk about that?
Yeah, so question is the RAG was semantic search. So I think these two are not competitors with each other. RAG is more a way to enhance the answers from real LLM, where semantic search or the vector search is the technology to support that. For example, they basically build RAG with vector search together. But however, if the question is like vector search have other use cases than RAG, yes, there are a lot of other use cases than that. For example, some of our previous work is doing the data mining on top of a large machine learning data set. For example, for Cruise, Waymo, those kind of autonomous driving company try to find special use cases within that. And this is actually in another few very high performance recommendation system as well. So that's where a very different side of old ML, not this new RAG or use case. Yeah.
Any more? Oh, here at the front. Do you have a question?
This is so dangerous.
Is a cushioning at least? It's my fault. Okay.
So the question about that, how do you compare LanceDB with Postgres and Pinecone?
Yeah, so that's a question that we need to answer for every meetup. And yes, so there are two, I don't know how many aspects of this. So one thing is like we try to be the SQLite of vector database. That means we have very low entry point for people to start to search. And we can simply host more than 1 billion vectors on one single laptop with a single digits millisecond latency search out of it. And I don't think any of other solutions provide such an easy way for people to start to try it. And on the higher end, that we are very confident that we have a few deployments to show very strong performance, much more than Postgres and Pinecone in that sense. That because there are two things one thing is that our index and all that is optimized for I/O access. So we push the scale of our cluster to the ratio between memory and storage to the whole full data set we can support. Active data we can support is much interesting, much appealing to customers, where we can still provide less than 50 or 100 millisecond latency. At that point, latency is not that important for our customers, where the costs become much more interesting for them. That's the thing. And also, we do support full text search and a few other stuff combined together. So hopefully that can be other wedge to sit in this market areas. Yeah. 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 Thanks. So question is that whether Lance will support compression similar to ORC or Parquet. And right now the disparity is significant to that aspects. Yes. So we have two aspects to talk about this. So one thing is like for Parquet and ORC, they try to support sequential scan, and we try to support the random access. So the compression that we can support is a relative limit to what they want to do. But we try to attack these problems through more advanced encodings, more like be the packing reference or ILE or something else to that. That's one thing. The other one is like because we are talking to multimodal data. The multimodal data itself is heavily compressed, video and image, and that is already heavily compressed. When we actually have internal benchmark against, say, store those stuff into Parquet itself and store in our stuff, the difference is you cannot actually see any difference from that. Yeah, that's our take right now. But we do. Actually, this week and next week, we have a few blogs will be published about our next version of Lance format design. They will talk about this as well. Yeah, sure. Sorry, I cannot hear you. Yes, okay. So currently, we don't think of us as a SQL engine, full SQL engine. We think of us as a storage support SQL, which means we support a decent amount of filters, but we don't support any like join, like UDF and all that, right? But underneath, we are using Data Fusion, Rust Data Fusion as our backend engine. So it's a standard implementation of SQL filters. So that's where we actually rely on, say, Trino, Spark, or something else to do joins. Yeah. Sorry, what's that?
One of the points that were in one
This thing? Sorry, can you repeat?
There is one of the section of Lance.
Yeah.
And it's focused on the vector search.
Yes.
Something like that. It's a light version.
Okay.
Light version of vector search.
It's a full version because we build vector index on disk, and our open source LanceDB can read exactly the same index format as our cloud offering, and that one including IVF PQ and IVF HSW with PQ and SQ implementation. That's very heavily optimized in terms of compression and performance and recall combined. That usually depends on what kind of compression rate you want, what kind of recall or latency you want. That's a little bit of trade-off that at least we don't see a good set of default setup that can be applied, like Postgres say, just create an index that everything works. We haven't seen a very good default one that can fit to everyone yet. So we have an instruction about what's the trade-off between those different algorithms and why you should choose this instead of that.
Question is, are your indices updated in real time, or do you run the job every so often to rebuild?
Oh, yeah. So question is whether our, especially vector index, is updated in real time. Answer is no. So our indexing is basically LSM kind of a structure. So we do have a huge snapshot than relatively smaller data. But when you do queries, we have this strong consistent mode that you just scan all of them with the one that you don't index. So basically that's like an in-flight updates. We don't index that. But there is a background job to periodically compact them into a larger one.